Namaskara. We will continue our discussions on knapsack problem and a correct greedy solution for the knapsack problem. In the knapsack problem, we are given n objects O1, O2, etc. On, and each object has got a unit amount of that object weighing W1, W2 and Wn. And each unit of the objects yield the profit as follows. O1 yields a profit P1, O2 and On a profit Pn. A unit amount of that object weighs W1 units and yields a profit P1. So, we will say that there is the weight and this is profit. Okay. And you have a knapsack, just a bag, which has a capacity m. You are allowed to carry a weight of m units in the knapsack. The maximum amount of an object that you can pick is 1 unit, okay, and single unit of O1 for example weighs W1 and it yields a profit P1, and you can take any fraction of that object, okay, to fill your bag. So, you may take a fraction x1 of O1, a fraction x2 of O2, a fraction xn, 0 less than or equal to xi is less than or equal to 1. Any arbitrary real number, a fraction of the object you can pick. And when you take object I with a fraction xi, it is going to weigh xi wi. So, for the choices that you have made, the total weight will be sigma xi wi I going from 1 to n, and this should be less than or equal to m. You can take objects in fraction, the maximum you can take is 1 unit, you can ignore, that is 0, or you can take any fractional amount of that object, and that will have a weight xi wi, because wi represents the weight of 1 unit of that object. So, xi units of that object will weigh xi wi, and when you take xi amount of xi units of object 1, you earn a profit of xi pi. So, sigma I going from 1 to n of this is called the profit. X can be visualized as a vector, x is a vector x1 to xn, and you can call this as profit px. The profit for an x vector is p of x given by this expression. P of x is sigma I going from 1 to n of xi pi. So, any set of xi's satisfying these conditions is called the feasible solution. It is a solution. You take that many fractions of those objects, it respects the condition, so that is a choice. Okay. It is a feasible solution. Any xi, x equals x1, x2, etc. xn with sigma xi wi less than or equal to m and 0 less than or equal to xi less than or equal to 1 is called feasible solution. It is a feasible solution. For every solution there is a cost associated with it. What is the cost here? The profit associated with x. P of x is the cost associated with this, which is sigma x I p I going from 1 to n. And what is the optimization problem here? Find x that maximizes P of x. Find that feasible solution which yields maximum profit. Because it is a profit, we would like to maximize. It is a maximization problem. So you can make a series of decisions. You can decide on first x1 and then on x2, then on x3. In this way you can make series of decisions and you can construct a solution. In general, the greedy algorithms are all incremental in nature. It will build a solution in several stages. Okay, greedy algorithms are incremental in nature. It builds the solution in what's happening? It builds the solution in several stages. Okay, it is a greedy algorithm. Every greedy algorithm will be incremental by nature and it consists of several stages, and in each stage okay, we make a locally optimal choice. This is just a point of view, a way to view in which the greedy algorithm works. The greedy algorithm consists of building the solution in several stages, and in each stage we choose a locally optimal solution. This series of locally optimal choice, we expect it to lead to a globally optimal solution. Okay. So, here consider the following example. We have O1 yielding profit of 24 and weighing 18, and O2 yielding a profit of 18 weighing 12 per unit, O3 yielding profit of 16 weighing 10, and the capacity M let us assume to be 20. 20 is the capacity of the knapsack. What fraction of O1 would you take, and what fraction of O2 would you take, and what fraction of O3 would you take to maximize the profit? Since the profit is to be maximized, the greedy strategy since the profit is to be maximized, since a possible greedy approach is choose the object with larger profit as much as possible. Okay? If you have an object that is giving larger profit, take that as much as possible, and that is going to give you more profit, and that is the intuition. You want to maximize profit, so take the object with larger profit as much as possible. For example, O1 has got maximum profit. I would like to take that as much as possible. Since 0 is less than or equal to x1 less than or equal to 1, I take this as much as possible. I will set x1 equal to 1. Maximum, you take that. So when you take maximum, the profit you are getting is x1 p1, that is 1 times 24, that is 24. But this is going to take up a weight of 18. So out of 20, 18 is consumed. You are left with only 2 more units available, because object 1 fills the knapsack, and what is leftover capacity is only 2 units. For the 2 unit, take the second object as much as possible. Since 0 is less than or equal to x2 is less than or equal to 1, x2 said to be 2 over 12, because unit weight is 12, 2 over 12 will have 2 units of weight. Okay? Therefore, x2 dot p2 is, x2 is 2 by 12, the profit is 18, and that would be 3. And now this is taking 18, this is taking 2, therefore 20 is used up, the full capacity is used up. X3 is just 0, 0 less than or equal to x3 less than or equal to 1, x3 must be 0, because there is no more capacity available in your knapsack. In the bag you can't fill any more, therefore you can't take the third object. That is done by setting x3 to be 0, that you are not taking that object, and the total profit is 27. Okay? Therefore, if we apply this greedy strategy, so this is a greedy strategy, you are greedy over the profit. You are greedy over the profit, and when you behave greedily over the profit and arrive at a solution, it yields a profit of 27. Is this optimal? This is not optimal. We are going to show, for example, a fraction half, half and half. Consider this fraction. This is x1, this is x2, and this is x3. Remember, recall the profit vectors are 24, 18 and 16. The weight vectors are 18, 12 and 10. So the weight of half of will be 9, the weight of half of this will be 6, the weight of this 5, together it will be 20. Your capacity is fully utilized. When you choose half of object 1 and half of object 2 and half of object 3 and fill your knapsack, it fills. How much profit you get? Half of 24 will be 12, half of 18 will be 9, and this will be 29. This is more than 27. That shows greedy by profit is not optimal. This implies greedy by profit is not optimal. There are solutions like this. There are solutions like this that give better profit. It gives more profit. Therefore, greedy is not producing a solution that is optimal. So, can we have a greedy strategy that would produce an optimal solution? The answer is yes, and you have to be greedy by profit per unit weight. Look into the quantities profit per unit weight. Whichever has higher profit per unit weight, take that as much as possible. In other words, the greedy strategy is take as much of the object as possible that has higher profit per unit weight. This is our new greedy strategy. I am greedy about a different parameter. Okay? So, consider the same example O1, O2, O3, and the profit are 24, 18 and 16. The weights are 18, 12 and 10. This is profit, this is weight. Profit per unit weight. For a weight of 18, you are earning a profit of 24. So, profit per unit weight P by W will be, this is roughly 4 by 3, so 1.33. This is 18 by 12 is 1.5. 16 by 10 is like 1.6. So, O3 has got very large profit per unit weight. Take this one as much as possible. For example, if this is x3, 0 less than x3, so take x3 equal to 1, all right, x3 you take as 1, and this is going to have a weight of 10 and it will yield a profit of 16. Okay, this is yielding a profit of 16, choosing x1 equal to. Out of 20, 10 is already consumed. You have taken 1 unit of O3, you have put in the bag, that has taken away 10 units, and the remaining 10. And for the remaining 10, I am going to take the next one with a higher profit per unit weight, that is O2. That is O2. So, I am going to take O2 as much as possible. How much I can take? I am left with 10. So, x2 is 10 by 12, because unit weight is 12, a fraction of 10 by 12 will weigh 10 units, and this is going to give me a profit of 10 by 12 times 18, 10 by 12 times 18. So, this is 3 and this is 2 and this is 5. So, this is going to give me a profit of 15, because 1 unit will give a profit of 18. 10 by 12, a fraction of 10 by 12 will yield the profit of 15. And now 10 plus 10 is 20. I have completely used up my, I cannot take any more, and therefore I am getting a profit of 31 in this scheme. If I go greedily by profit per unit weight, I am getting a profit of 31. But is this maximum? What if there is some other fractional combination that gives a better profit? Or is it just for this example, or is it true for any input, any arbitrary input? So, all this can be confirmed only when you give a formal proof. The answer is yes, this is going to give you the maximum profit. No other combination of fractions will give you a profit more than this particular greedy strategy. Whatever is the input, whatever is the output that is constructed under this greedy strategy, that vector will have the maximum profit. Okay? So, we are going to prove that formally. Before that, we will introduce certain notation. We will assume that we have object 1 which has got a profit P1 and a weight W1. Object 2, it has got profit P2 and weight W2, and object N, Pn, Wn. We will assume that the numbering is done in such a way that P1 by W1 is greater than or equal to P2 by W2 is greater than or equal to Pn by Wn. Because this is the order in which our greedy algorithm selects as much as possible. So, our greedy algorithm is going to take O1 as much as possible. After that, it will take O2 as much as possible, because that is the next object with the next profit per unit weight value. Therefore, my greedy solution will have the following form. I am going to take O1, x1 will be 1, x2 will be 1 as much as possible, and then there comes a stage where I will not be able to take 1 or probably a fraction, and after that I will not be able to take anything because I have used my capacity fully. So, this is going to happen in the kth object. This f is less than or equal to 1. Okay, f is less than or equal to 1. That is the last object I could take, and that would fill the capacity. So, this is how my greedy solution, which is x1, x2, etc., xk plus 1, xn is going to look like. My greedy solution will have the following form. Take as much as possible means you can take 1 unit. If it is possible for you to take 1 unit, take 1 unit and go to the next object. If you could take 1 unit of that, take that much. In this way, you will come to a stage where you will not be able to take 1, probably a fraction of it, and you take that much and then you stop the process. After that, everything is going to be 0. You can't take any more object. Therefore, this is the form of greedy solution under our assumption that our objects are labeled. You can call whatever is that object that has got maximum P1 by W1 as O1. Whatever is that object that has got the next Pi by Wi value as O2 and so on. Therefore, our greedy algorithm is going to pack the objects in this order, and therefore the greedy solution is going to be like this. And what is the profit that you get? P of x equal to sigma xi pi, I going from 1 to n. This is the profit that you have got using greedy solution. Take any other solution, and you also have the following: sigma x I wi is equal to m. Your capacity is fully utilized. If the capacity is not fully utilized, you can take some more, right, and you can increase the profit. That this is maximum means the capacity is fully utilized. Sigma xi wi is m. Any other solution, you call it as a y vector, that is fraction y1, y2, etc. yn, 0 less than or equal to yi less than or equal to 1, sigma yi wi is less than or equal to m. This is property of any solution. The values will be less than or equal to 1, and it's a solution, feasible solution. It respects the weight constraint. And what is the profit that you get? Py. What is the profit you get? Py is sigma yi pi. This is the profit you get. What is that we want to show? We want to show that Px is greater than or equal to Py. Px is greater than or equal to Py for any y, for any feasible solution. With every feasible solution you are going to get some profit, but the profit you get based on the greedy solution is optimal. It is going to be larger than any profit that you would obtain through any other solution. This is what we have to prove. Therefore, we must prove Px is greater than or equal to Py. So, how do we prove that Px is greater than or equal to Py? Since these are all positive numbers, okay, you can show, for example, Px by Py is greater than or equal to 1. This will show that Px is greater than or equal to Py. There is another way. You can show that Px minus Py is greater than or equal to 0. This will also show that given Px and Py are all linear combination, we will take this option. In order to prove that Px is greater than or equal to Py, we will show that Px minus Py, which is equal to sigma I equal to 1 to n of I equals 1 to n of Pi times xi minus yi. Px minus Py is exactly this expression. I want to show Px minus Py to be greater than or equal to 0. It is sum of several terms, okay, and sum of all these terms are greater than or equal to 0. That is what we have to show. But what do we know? What we know is this. What we know or what we have is the following: sigma xi wi equal to m, sigma yi wi is less than or equal to m. So, when you subtract sigma wi xi minus yi is greater than or equal to 0. This is what we have. You subtract, okay. Then this is what we have, but this is what we want to show. What is that we want to show? We want to show that this quantity is greater than or equal to 0. Okay, let us not cram it. This is only a thought process. We want to show that this is greater than or equal to 0, but look what we have, somewhat similar expression. This is very close to what we want to show, except that instead of pi we have a fact relating wi. So, I bring wi into the scene as follows. This is equal to sigma I equal to 1 to n of pi by wi times wi times xi minus yi. It is the same. I have just multiplied and divided the ith term by wi. So, I have something like wi xi minus yi is in the expression, but unfortunately every term is multiplied by a different value. It is multiplied by a different value. As a thought experiment, okay, just as a thought experiment, imagine I am able to show that this is greater than sigma I equal to 1 to n of some constant c, positive constant c, wi xi minus yi. Suppose I am able to show this, that is I am able to replace them with some constant. Then I can pull out the constant c. Let us say I am able to replace each pi by w by a constant c. Then I can write an inequality of this kind, which would mean, this would imply this is greater than c times sigma I equals 1 to n of wi xi minus yi. This we know is greater than 0. If c is a positive constant, you know that the whole thing will be greater than 0. So, this is what I am going to work towards. In order to build a proof, I am going to figure out a constant, a positive constant, using which I will have an inequality of this type. Okay? So, which constant will work so that I can have an inequality as outlined here, all right. So, let us see a very interesting constant that is going to work for us, and we will use that constant and complete the proof. Okay. So, we make the following observation. If you look into the term sigma I equals 1 to n of pi by wi xi minus yi, consider this, you break them into 3 parts, okay, you break them into 3 parts. The first part is this is equal to sigma I going from 1 to k minus 1 of Pi by Wi xi minus yi, then the kth term Pk by Wk of xk minus yk plus sigma I equals k plus 1 to n of Pi by Wi times xi minus yi. Terms I have broken into 3 parts. Why did I break this into 3 parts like this? If you look into x, what is the form of x? X is like 1, 1 up to k minus 1, then you have 0 after this. Y is y1, y2, yk, yk plus 1, yn. Alright, and 0 less than or equal to yi less than or equal to 1. Therefore, up to yk minus 1, all these things are positive, because xi is 1, if y is 1, that is 0, that term will not be there, but if it is less than 1, this is a positive quantity. Xi minus yi is a positive quantity. Xk minus yk could be anyway, we do not know how their relative values are, let us not worry about it. In this xi is 0, you can see that when I equal to k plus 1, this is k plus 1, all these are 0. So xi's are 0 here, yi's are some positive number, therefore all these things are negative. That means this is less than 0. All these expressions are less than 0. So if I have 2 numbers, positive numbers multiplying, if I want to make it smaller, I can make one of them smaller. For example, if I have 5 times 10, that is equal to 50. Okay, we will write it here aside. Suppose you have 5 times 10, that is 50. You reduce 5 to 3, 3 times 10 will be 30, so the value is reduced. The value is reduced. You reduce 5 to 3, the value is reduced. So here I can reduce this to Pk by Wk. Pk by Wk. Why this is a reduction? Remember, P1 by W1 is greater than or equal to P2 by W2 is greater than or equal to Pk minus 1 by Wk minus 1 is greater than or equal to Pk by Wk. So all these values are larger. So I going from 1 to k minus 1, Pi Wi, they are all larger than this. So when I replace Pi by Wi by Pk by Wk, I am reducing the value. Okay, term by term it becomes smaller. When I replace Pi by Wi, term by term it becomes smaller. Okay. Therefore, in this part, in the first sum, I can replace Pi by Wi by Pk by Wk. Now, Something very interesting is happening in the second part, in the second sum. Each term is negative. When you have a positive number and negative number multiplying to give a negative number, Pi by Wi is profit per unit weight, positive number. So that is like 5 times minus 10, that will be minus 50. Now this 5 must be increased to 7, 7 times minus 10 will be minus 70, only then the value will become smaller. So you have to increase the number, you should not reduce, you should increase Pi by Wi to make this term smaller. So to what value I can increase? Now you can continue to see that Pk plus 1 by Wk plus 1 greater than or equal to Pn by Wn. Again I can replace this by Pk by Wk, that will increase the value like from 5 to 7. The other term is negative. So the positive value is increased, the negative value is same, things have become smaller. In other words, when I am replacing Pi by Wi by Pk by Wk, the right hand side becomes smaller. Term by term it becomes smaller. It is becoming smaller in the first sum in a different logic. It is becoming smaller in the second sum in a slightly different logic, but they do become smaller term by term. Okay? This is what we are going to use. In other words, the constant Pk by Wk will work for us. So we will now summarize. Px minus Py is equal to sigma I equals 1 to n of Pi times xi minus yi. This is equal to sigma I equals 1 to n of Pi by Wi times Wi times xi minus yi. This I write as sigma I equals 1 to k minus 1 of Pi Wi times Wi xi minus yi plus Pk by Wk of Wk of xk minus yk plus sigma I going from k plus 1 to n of Pi by Wi times Wi xi minus yi, and this is greater than or equal to, I am going to replace everywhere Pk by Wk, sigma I equals 1 to k minus 1 of Pk by Wk. I have replaced this times Wi xi minus yi plus the Pk term plus sigma I equals k plus 1 to n of Pk by Wk of Wi. Pk by Wk Wi xi minus, it is not this is equal to, I can take Pk by Wk common out and sigma I equals 1 to n of Wi xi minus yi, and this is greater than 0 and this is greater than or equal to 0, therefore this will be greater than or equal to 0. In other words, Px minus Py is greater than or equal to 0. That is, Px is greater than or equal to Py, and this means greedy solution is optimal. Greedy solution is optimal. So, we have to do some crucial, here it has been messed up. So, we need to let me rewrite this part. This is greater than or equal to sigma I equals 1 to k minus 1 of Pk by Wk times Wi times xi minus yi. We have seen that this replacement reduces the value term by term, then Pk by Wk, this is the kth term, I am not touching this at all, xk minus yk plus sigma I going from k plus 1 to n of Pk by Wk. Here also I am replacing Pi by Wi by Pk by Wk, okay, is greater than or equal to this. Now, I can take in the next page, as you can see, it is now coherent, okay, it is Pk by Wk sum and so on. So, what we have argued that term by term replacing Pi by Wi by Pk by Wk reduces the value, and that completes the proof. This is the formal proof that the greedy by profit per unit weight works. Greedy by other parameter did not work, but greedy by profit per unit weight works. Okay. It is not just for that example. For any instance, we have given a generic formal proof, and this is how you should prove the correctness of the greedy strategy. Okay. And there are a couple of other interesting techniques for proving the correctness of greedy strategies, and we are going to explore them in our subsequent discussions. I conclude this session at this point. Thank you.